This section is on linear optimization, which is the mathematical process for finding the maximum or the minimum value of a situation, given real-life restrictions and limitations. So this process was developed during and after World War II for maximizing supplies and minimizing costs. Since then, the process has been adapted to industry for maximizing profits and minimizing loss, as well as to the health field to plan diets that minimize cholesterol intake. So there's a lot of terminology in this section, and we're going to need to know what all of these terms mean. So we have the objective function. This is the expression describing what is being maximized or minimized. So are we trying to maximize profit? Are we trying to minimize loss or minimize cholesterol? So the objective function, this is the expression which describes what we're trying to maximize or minimize. Next we have the constraints, and these are linear inequalities that model real-life limitations and restrictions. So we did work with linear inequalities in the previous section, so this is very much related to that. Next is the feasible region, which is the shaded region formed by the constraints. And points within the feasible region work in all of the original inequalities. So in the previous section we were graphing inequalities, and we had to shade above and below, and then we had the intersection of the shadings. Here we have enough linear inequalities that the intersection of all of the shadings actually forms a shape, and that shape is the feasible region. Lastly, we are dealing with corner points, and the corner points are really the corner points of the feasible region. And the corner points are the candidates for giving the max or the min. So these points are plugged into the objective function to find the maximum or the minimum value. So if we look at number 1, this is our objective function. So this is what we are trying to maximize. So we want to pick values for x and y to get the highest value out of this equation. However, x and y have to be constrained by the feasible region, meaning they need to be inside of the feasible region. So we have a lot of different points of interest here that we're going to talk about. So is -5, -3 in the feasible region? And the answer is no. So immediately, we do not care about it. Is the point 8, 9 in the feasible region? The answer is no. So we do not care about it. Is 2, 4 in the feasible region? Yes, it is. So it's in the shading. Is it a corner point? The answer is no. So even though it works within all of the original inequalities, so even though it's within the feasible region, because it's not a corner point, it's not going to give us the maximum value. So we do not care about it. Is the point 0, 0 in the feasible region? Yes, it is. So if it's on the line, it counts. Is it a corner point? Yes. Does it yield the maximum? So the point 0, 0, we plug into the objective function and we get 0. And that is not the maximum value here. So the answer is no. Is the point 0, 8 in the feasible region? Yes. Is it a corner point? Yes. Does it yield the maximum? So 0, 8, when you plug it in, we get 40. And 40 is not the highest value here. So no. Is 4, 9 in the feasible region? The answer is yes. Is it a corner point? Yes. Does it yield the maximum? So if you plug in 4, 9, you get 73. And that is the highest value here. So yes. So the maximum is 73 at 4, 9. So 73 is the highest that the objective function can go. So that would be our answer, but I do want to finish the question about 8, 0. So is 8, 0 in the feasible region? Yes. Is it a corner point? Yes. Does it yield the maximum? No, because if you plug in 8, 0, you get 56. And we know that the maximum is 73.